Alright, okay. So today we're going to be going over number theory. So let's start with modular. So let's start with inverses, modular inverses. So I'm sure you guys know this, but just as a quick review, right? A mod B is the remainder when A is divided by B, right? Are you guys familiar with this modular arithmetic? So we define the inverse of A, mod, so generally we're going to have mod M. So the inverse of A, which is we always write it as A negative 1. This is defined as the number between, so A negative 1 is between 0 and M, such that A times A inverse equals 1 mod M. So the inverse of A with respect to mod M is defined as A to the power of negative 1, and it's such that A times A inverse equals to 1 mod M. Alright, and as you can see, A inverse is also it's under mod M, so it's between 0 and M, as would be. And so with the inverse, so for prime, for whenever M is prime, the inverse is guaranteed to exist. So inverse always exists, and it's unique. So for any A, there's exactly one inverse, and it's unique. And then this also is true if GCD of M and A equals 1. Then A inverse exists and it's unique. So if M and A are relatively prime, A inverse exists and it's unique. But if A and M are not relatively prime, then you can see that it clearly won't work. So A inverse does not exist in this case. So A inverse does not exist, because if A inverse did exist, so if M and A share a prime factor P, so GCD M comma A equals P, then A times A inverse is always divisible by P, and so this can never equal 1 mod P. So the inverse only exists if the GCD of M and A is 1. Right? So there's a rule with inverses, and this rule states that A plus B is congruent to AB times A inverse plus B inverse mod P. So from now on, instead of working with M, we're going to work with P, where P is prime, right? And so basically, this rule, it shows us that we can work with inverses as if they were fractions. So if we write this as a fraction, so AB times 1 over A plus 1 over B, then this equals, obviously, A plus B. And that's what we would expect. So whenever we're working with inverses, we can kind of treat them as fractions. So, for example, A inverse plus B inverse, this is all under mod P. Right, we can write this as 1 over A plus 1 over B, and then if we you get a common denominator, this is equal to A plus B over AB. And this is equal to A plus B times the inverse of AB, mod P. So and this relationship is always true. So we can work with these inverses kind of like fractions. So an example of where this would be useful, let's consider the problem. So let P be greater than 5. So for any prime greater than 5, show that there is an n such that P divides 20 to the power of n plus 15 to the power of n minus 12 to the power of n. Alright, so in this example, we're going to use Fermat's theorem, Fermat's little theorem, which states that a to the power of p minus 1 equals 1 mod p, where a is not divisible by p. And so this, I'll prove this on the next, in a couple minutes. The proof of this lies in inverses. But for now, let's take this to be true, and let's use that here. So for n, what we can choose is, consider n equals to p minus 3. So if n equals p minus 3, then 20 to the power of p minus 3 plus 15 to the power of p minus 3 plus 12 or minus 12 to the power of p minus 3. This equals to 20 squared inverse, right? Because 20 to the power of p minus 1 equals to 1 mod p, and so 20 to the power of p minus 3 equals to 1 over 20 mod p, or 1 over 20 squared. So if we use this here, so this equals to 1 over 20 squared plus 1 over 15 squared minus 1 over 12 squared. And you can check that this equals 0. So 20 to the power of p minus 3 plus 15 to the power of p minus 3 plus 12 to the power of p minus 3 equals 0. And then 0 is obviously equal to 0 mod p. So for n equals p minus 3, this is always true. So this is an example of where using inverses as fractions might be useful. Right, so I promised I would prove Fermat's theorem. So Fermat's little theorem basically states that a to the power of p minus 1 is congruent to 1 mod p. And so the proof of this, we start with, consider the numbers a, 2a, 3a, all the way to p minus 1 times a. So first we claim that, so our first claim is that no two of these are congruent under mod p. So we claim that essentially what we're saying is ai is not congruent to aj mod p. And this is obviously true. We can just divide the a from both sides. And so I equal to j mod p. So if I is not equal to j, then ai is not equal to aj mod p. Right? So none of these are the same mod p. So each of these, a, 2a, 3a, are a different value under mod p. And there's exactly p minus 1 of them. So that means these values must be some permutation of 1, 2, 3, all the way to p minus 1 mod p. So the set a, 2a, 3a, all the way to p minus 1 times a must be equal to the set 1, 2, 3, all the way to p minus 1. Right? And so, if we take the product of all the elements of each set, they must be equal. Right? This is all under mod p, again. So we take the product of each, of all the elements. So on the left side, we'll have a to the power of p minus 1 times 1 times 2 times 3, all the way to p minus 1. And this is equal to 1 times 2 times 3, all the way to p minus 1 mod p. And we can divide this from both sides because it's not divisible by p. And so we ended up with a to the power of p minus 1 equals to 1 mod p. Alright, so this is Fermat's little theorem. And then we also have Euler's theorem, which states that a to the power of phi of n equals 1 mod m. So note here that we're using m, not p, so phi of m. So this is true for any m. It doesn't have to be prime. And phi of m, just in case you're not familiar with this, is essentially equal to, so if m if the prime factorization of m is p1 to the a1 times p2 to the a2 all the way to pk to the power of ak, then 5n equals to, or 5m equals to m times 1 minus 1 over p1 times 1 minus 1 over p2 all the way to 1 minus 1 over pk. So you can see if m is prime, then Euler's theorem reduces back down to Fermat's little theorem, right? So this is really useful when we're considering powers of numbers under mod m. And one more technique to consider is when we're using Euler's theorem, it's always helpful to instead split m into its prime factorization terms. So for example, right, this is AIME. A lot of things are going to be asking you for mod 100. So if we're looking for like 3 to the power of, or if we're looking for, say, 12 to the power of 50 mod 100, it would be easier to consider splitting this into 12 to the power of 50 mod 8 and 12 to the power of 50 mod 125. All right, one more thing I forgot to mention here is that Euler's theorem only applies if GCD of A and M equals 1. Right? So now if we consider this is obviously just 0, mod 8. And this we can find using Euler's theorem. And then we can combine this using Chinese remainder theorem to get our final answer. All right? We'll do one more technique, which is called lifting the exponent. So first we have a definition. So we're going to define the highest power of p that divides n as v sub p of n. This equals to highest power of p that divides n. Right? So, v sub 3 of 12 will equal 1. V sub 2 of 12 will equal to 2. And v sub 5 of 25 equals to 2. Right? So it's just the highest power of p that divides n. And usually p is prime, but it can also not be prime. But usually it's prime. Alright? So the theorem of lifting the exponent basically states that Vp of a to the n minus b to the n equals Vp of a minus b plus Vp of n. Only if p divides a minus b and p does not divide a or b. So this is useful for, this is the theorem of lifting the exponent. And so a couple of examples where this might be true. So consider the number 999 all the way down to, so there's 15 nines. So what is the highest power of 3 that divides this? Well, obviously 9 divides this, right? But does 27 divide this? And then what about 81 and so on? So it would be hard to do the long division on this, but here we can just use lifting the exponent. Because this number, let's call this n, this is equal to 10 to the power of 2015 minus 1, and that's the same as to the power of 2015. And we want to find v3 of n, and so this would be v3 of 10 minus 1 plus v3 of 2015. And this is obviously just 0, and this is 2. So our answer is 2. So it makes it really simple. Alright, so let's look at another example. So consider this. So suppose A1, so we're going to define a sequence. A1 equals to 2011, and AN equals to 2012 to the power of AN minus 1 for all n greater than 1. So what is we want to know what is VP of A2012. Well, let's use lifting the exponent. So if we take this, VP of AN is going to equal VP of 2012 minus 1. We want to know, P here is 2011. I forgot to say that. So we want to know V 2011 plus VP of AN minus 1. So this equals to, 1 plus VP of AN minus 1. So that means that V 2011 of 2012 is going to just equal to, so V 2011 of A1 equals to 1, and then you're just going to keep adding 1, so our answer is 2012. Alright, so that's kind of some cases where lifting the exponent might be useful, but one thing to keep in mind when lifting the exponent is always want to make sure that P is not equal to 2. Because if P is equal to 2, then there is a different form of lifting the exponent. So if P equals to 2, then if P equals to 2, and 4 divides A minus B, then you can apply normal lifting the exponent. So we're going to call this LTE. And then if P equals to 2, but 4 does not divide A minus B, then we have to use a different form of lifting the exponent, which is V2 of AN minus B to the power of N equals to V2 of A minus B plus V2 of A plus B plus V2 of N minus 1. So we have to keep in mind that pitfall of P equals to 2. And then another common error is not checking whether P divides A minus B. So going back to lifting the exponents, this is a major assumption. P divides A minus B, and P does not divide A comma B. So if these two do not, if either of these do not hold true, then you can't use lifting the exponent. Alright? So that's enough on theory. Let's look at the problems. So I compiled about 11 problems. I think you can see them in the Google Classroom. Alright. Whoops. Okay. So you guys want to go through the problems? So I ordered them in difficulty. So 1 is the easiest and 11 is the hardest. So do you want to go backwards or forwards? Easiest to hardest or hardest to easiest? Okay, well one person said, okay. Okay, well 2 people said forward, 1 person said backwards. So I guess it's forwards it is. Okay, so open up the handout that's in the classroom and follow along. So I can't show the problem and the Jamboard at the same time. So I'm just going to show the Jamboard, and then you can read the problem on the handout. So let's start with the first problem. How do you send your answers? You can just write it and take a picture, or just put it in a document and just put it in the classroom or in the chat if you want. Alright, so let's go, let's look at the first problem. So find the number of 7 tuples of positive integers that satisfy the following systems of equation. So basically we have ABC equals to 70, CDE equals to 71, and DEF equals to 72. So we always want to first try the basic rules of divisibility. Before we go into like some of the more advanced theorems that I talked about, we always want to try basic rules of divisibility and prime factorization. Those are going to be our most used techniques. So the first thing we notice is that here C divides 70, and here C divides 71. So this means that C divides the GCD of 70 and 71. And the GCD of 70 and 71 is obviously just 1. So if C divides 1, that means C equals to 1, right? Now, if we look at E, if we look at E and D, it should be E, F, G. Right, if we look at E, the same thing holds, right? E divides GCD of 71 and 72. So E also equals 1. And so if E and C are 1, then D is obviously 71, right? So we already fixed 3 of these. So now if we keep going, so we have AB equals 70, and we have FG equals 72. So these are the only, these are 4 variables are not fixed yet. So what are the possibilities here? So A and B are just factors of 70, and F and G are just factors of 72. So to count the number of factors of 70, 70 equals to 2 times 5 times 7. So the number of factors is 2 times 2 times 2, which is 8. So there's 8 possibilities for A, and each possibility for A gives 1 possibility for B. So it's 8. And then F and G are the factors of 72, right? 72 equals to 2 cubed times 3 squared. And so the number of factors is just 4 times 3, which is 12. And so this gives 12. And so the total number of possibilities is 8 times 12, which is 72, or which is 96. Right? So the answer to the first one is 96. Alright, let us continue. So now let's move on to problem 2. So this idea of bases is really important in AIME. Right? A positive integer n has a base 11 representation, ABC, and a base 8 representation, 1 BCA. So find the least such n in base 10. So whenever you're confronted with this base type problem, you always want to first convert everything into base 10. So BCA, or we have ABC in base 8. This equals to 64A plus 8B plus C in base 10. And then we have 1 BCA in base 11. Or whoops. This is in base 11. This is in base 8. And so we have 121A plus 11B. And so this equals in base 8. This is 512 plus 64. Oops. Alright, 64B plus 8C plus A. Alright? And so these base 2 or base 10 representations are equal. So we have 121A plus 11B plus C equals to 512 plus 64B plus 8C plus A. And if we collect the terms, we'll end up with 120A equals to 512 plus 53B plus 7C. Alright, so we have to first consider the bounds on this. Right, B, C, and A are all digits in base 8. So A, B, and C are at most 7, and it's at least 0. Right? Now we also have 120A is at least 512. So that means A is at least 5. Right? A can't be 4. So, and we're trying to find the smallest such n. So the smallest such n, we want to minimize first A, then B, then C. Right? So if we start with minimizing A, let's just try A equals to 5. So if we try A equals to 5, this gives us 600 equals to 512 plus 53B plus 7C. And so this gives us 88 equals to 53b plus 7c. Alright, so now we've fixed a, so let's minimize b next. So if we try b equals 0, that doesn't work. Right, that gives c is not even an integer. And so if we try b equals to 1, then this gives c equals to 5. Right, and so this works. And so since we started minimizing it, this must be the smallest possible value. So smallest possible value is a equals to 5, b equals to 1, and c equals to 5. And you always want to read the problem correctly. It's asking us for n in base 10. So that's going to be 5 times 121 plus 11 times 1 plus 5. And so this equals to 605 plus 16, which is 621. So this is our answer. Right? Any questions so far? Alright. So that was some relatively easy. Oh, whoops. Interesting. Alright, so that was a relatively easy 2 problems. So now let's look at something a little bit more challenging. So the third problem. Let m and n be positive integers satisfying the conditions m plus n. So the GCD of m plus n and 210 is 1. M to the power of m is a multiple of n to the power of n. And m is not a multiple of n. So this is a little bit more theoretical. So we have GCD of m plus n, 20, or 210 is 1, right? So that means m plus n is not divisible by 2, 3, 5, or 7. And then we also have n to the power of n. N to the power of n does not divide m to the power of n, or sorry, it does divide m to the power of m. And then we have n does not divide m. Right? So the best way to deal with these types of problems is we start with prime factorization. So let's look at the prime factorization. So let's suppose n equals a general prime factorization, which is always, I always write it as p1 to the power of a1, p2 to the power of a2, all the way to pk to the power of ak. And m equals to, call this q1 to the power of b1, q2 to the power of b2, and so on, right? Okay. So if n to the power of n divides m to the power of m, that means every prime factor in m to the power of m must be a prime factor in n to the power of n. So any prime that divides this number must also divide this number. And so every prime that divides m to the power of m is just every prime that divides m. So the primes that divide this are q1, q2, and so on. And this must be, all of these must be prime factors of n to the power of n. And the prime factors of n to the power of n are just the prime factors of n, right? So the prime factors of n to the power of n are p1, p2, p all the way to pk. So that means that q1 through qk, this must be a subset of p1, p2, all the way to pk, right? So this must be a subset of this. So every prime factor of m is also a prime factor of n. So now, how can the second condition be satisfied if that's true? So if n does not, so if every prime factor of m is also a prime factor of n, then how can it be that n does not divide m? Well, either n has extra prime factors, which could be possible, or m has prime factors that have, or m for the powers of q in m are less than the corresponding powers of q in n. So for example, if one of the q's was 2, right, maybe in m it's 2 to the power of 3, and in n it's 2 to the power of 4, in which case this would not divide. So that's the only possibilities. Okay. So where might we go from here? Any ideas? Okay, so one more thing to notice. So what happens if n has a prime factor? What happens if all of these coefficients, a1, a2, all the way to ak, are 1? Well, if all of them are 1, then can this ever be possible? Well, that can never be possible, right? So if all of these conditions are 1, then n must have extra prime factors. So this possibility is not possible. So where n has a prime factor of a higher power than the corresponding prime factor in n. Okay, so that's a possibility. Or one or more of these is not 1. So that's a possibility. Okay, one more thing to consider. We haven't considered this first case yet. So where might this come into play? Well, both m and n are divisible by q1, q2, all the way to qk, right? So that means their sum, m plus n, is also divisible by all of these prime factors, q1 all the way through qk. Correct? So if m plus n is divisible by that, then that means that none of these prime factors can be 210. Or none of these prime factors can be prime factors of 210. Because, so that means that none of them can be 2, 3, 5, or 7. Can't be 2, 3, 5, or 7. Which means they must obviously be at least 11. And we want to find the smallest possible value of m plus n. So we might as well start with only one prime factor. So we might as well start with k equals 1 and q1 equals 11. We might as well start there, right? We want to find the smallest. So let's start there. Right, so I can't make any more Jamboards for some reason. So I'm going to make a new Jamboard. Hold on. Alright. Let's go back to Jamboard. Alright. While I'm making a new Jamboard, consider the problem. Alright, so we stopped off with, we're going to try the possibility k equals to 1 and q1 equals 11. So we know that m equals to 11 to the power of something. So it's a multiple of 11, 11k, and k can't be divisible by 2, 3, 5, or 7, right? M is 11 times k, and so n, so what could be the smallest possible value of n? Well, n obviously has to be divisible by 11, and it has to be divisible by another prime factor, or it could be 11 squared, right? It could be 11 to the power of 2. Okay, so if we tried this, right, 121. I forgot to mention one more thing. So let's go back to the previous Jamboard. But right, so I said that every prime factor of m is also a prime factor of n, but the reverse also holds true. Right, every prime factor of n is also a prime factor of m because n divides m. Right, so n can't have any prime factor that m doesn't have. Sorry, I reversed this. It should be P1 through Pk is a subset of Q1 through Qk. There we go. That's much better. Alright. And so that means that P1 through Pk cannot be 2, 3, 5, or 7. Right? And so we're starting with k equals to 1 and P1 equals to 11. Okay, there we go. Let's go back to the other Jamboard. Alright, so we started with m is divisible by 11, right? And we know that m can't be divisible by any other prime, any single digit prime, but it can be divisible by other primes. So it could be divisible by, say, 13, 17, or so on. But the smallest possible value is obviously if it's just divisible by, or if it is just 11 squared, right? It can't be just 11, otherwise n would divide m. So that means it has to be at least 11 squared. So let's consider this possibility. So n is 11 squared, and m is 11k, or 11 to the power of k. So n to the power of n equals 11 to the power of 242. And this divides m to the power of m. And m to the power of m equals 11 to the power of m times k to the power of m, right? And so 11 to the power of m must be divisible by 11 to the power of 242. So that means 242 must be at least m. Or m must be at least 242, correct? So m is at least 242. Alright, so m must be at least 242, and it must be a multiple of 11. So what's the next multiple of 11 after 242? Right, we could have 253. So if we have 253 and 121, does that work? Right, thank you for listing them out. So we have 253 and 121. So this m plus n equals to 374. And this is divisible by 2, as is 210. So this is not going to work. And so you can see that any odd m is also not going to work. So let's try 264 and 121. So this gives m plus n equals to 385. This is divisible by 5, as is 210. So this is not going to work. After that, we have 275, which we already established won't work. And then we have 286. So 286 plus 121, that gives 407. And this is not divisible by 2, 3, 5, or 7. So GCD of 407 and 210 equals 1, right? And that's exactly what we wanted. Okay, so that's a possibility. So what's the next case? So next case would be n equals to 11 times 13, right? In which case m would be 11 times 13k. But in this case, n divides m. So this is not possible. So the case after this would be either 11 times 15 or 13 squared, right? 11 times 15 doesn't work for the same reason, because it would divide m. So the next possible case is n equals to 13 squared. So if n equals to 13 squared, then m equals to 13k. And in this case, right, k is at least 2. So m, or sorry, alright, okay. Right, 13 squared divides 13 squared to the power of 13 squared is 13 to the power of 2 times 13 squared. And this divides m to the power of m, which equals to 13 to the power of m times k to the power of m. So we have, or 13 to the power of m. So we have m is at least 2 times 13 squared. And so if m is at least 2 times 13 squared, then m plus n is at least 3 times 13 squared. And this is already greater than 407, which is what we had gotten up here. So the smallest possible value of m plus n in this case is 407. Alright, any questions on that? Okay. Alright, so let's go to the next problem. So call a positive integer n k pretty if it has exactly k positive divisors and n is divisible by k. So for example, 18 is 6 pretty. Let s be the sum of positive integers less than 2019 that are 20 pretty. Find, and it should be s over 20, not s20. Okay. Alright, so let's consider this. So any 20 pretty number is divisible by 20. Right, so let's write the prime factorization of such a number. So it should be 2 squared times 5 squared, or times 5 times k. Right, and it has 20 factors. And to count the number of factors, it's easiest to write the prime factorization. So let's write this, or rewrite this, as 2 to the power of 2 plus a times 5 to the power of 1 plus b times some more numbers, k prime, so on, right? So here we have a comma b are at least 0, right? And so let's consider the first case, which is when k prime is just 0. So there's no, or it's 1. There's no other prime factors to n. So n is only divisible by 2 and 5. So in this case, we have the total number of factors is 3 plus a times 2 plus b, and this is equal to 20, right? So now this is just casework. So this could be, right, this part is at least 3, this part is at least 2. So this could be 4, 5, 5, 4, and 10, and 2. This gives a and b as, actually we don't even need a and b, because this gives n as 2 to the power of 3 times 5 to the power of 4, 2 to the power of 4 times 5 cubed, and 2 to the power of 9 times 5. So these are all 20 pretty numbers. And we can check that this is actually greater than 2019, so we can't consider that. And this is also greater than 2019. But this is less than 2019, so we got 1. Okay, so that was the first case, was when there's no other prime factors. So what happens if there's exactly one other prime factor? So n equals to 2 to the power of 2 plus a times 5 to the power of 1 plus b times p to the power of c. So in this case we have, right, 2 plus a, or 3 plus a times 2 plus b times 1 plus c equals to 20. And this is at least 1, this is at least 2, this is at least 3, right? And because this is at least 3 and this is at least 2, their product is at least 6. So that means 1 plus c can't be greater than 3. It can't be 4 or anything more. So 1 plus c is at most 3. So the only possibilities are this is equal to 1, this is equal to 2. But if this is equal to 1, then c equals to 0, and we already counted that case. So that case is already counted. So the only other possibility is if c equals to 2, or if 1 plus c equals to 2. Then we have 3 plus a times 2 plus b must be 10. The only possibility is 5 and 2. And so this gives us n equals to 2 to the power of 4 times 5 times p, where p is a prime number. Any prime number seems to work. Okay, and then we have the next case would be if there's 2 prime numbers. So 2 to the power of 2 plus a, 5 to the power of 1 plus b, p to the power of c, and q to the power of d. The total number of factors is 3 plus a times 2 plus b times 1 plus c times 1 plus d. And since c and d are at least 1, right, this is at least 2, this is at least 2, this is at least 3, or this is at least 2, sorry, and this is at least 3. So the whole product is at least 3 times 2 times 2 times 2, which is 24, and that's greater than 20. So this case has no solutions. And then if we keep adding prime factors, you can see clearly that there's going to be no more solutions, right? So we've found all our solutions. So our solutions are 2 to the power of 4 times 5 cubed, and then 2 to the power of 4 times 5 times p, where p is a prime number. So p could be, alright, so let's bound this first. So what is the bounds on p? So this must be at most 2019. Right, so we have p, ADP is at most 2019. So if p is at most 250. Or p is at most 25. That's better. And so we have p equals to 2, 3, p can't equal to 2. So p can't be 3, it can't be 5, 7, 11, 13, 17, 19, and 23. So our solution here is, our answer would be 2 to the 4th times 5 cubed plus 2 to the 4th times 5 times 3 plus 7 plus 11 plus 13 plus 17 plus 19 plus 23 all over 20. And that's easy to compute, right? So I'll leave that up to you. Alright, any questions on that? Okay, alright, so let's go to the next problem then. So for positive integers n and k, define n to be k-nice if there exists a positive integer a such that a to the power of k is exactly n positive divisors. Find the number of positive divisors less than 1000 that are neither 7 nice nor 8 nice. Alright. Okay, so a number is k-nice if there exists a positive integer such that a to the k has exactly n positive divisors. Alright, so as always, you always write everything in terms of its prime factorization first. That always helps you find things. So a to the k equals something like p to the power of, or p1 to the power of k times a1, p2 to the power of k times a2, all the way to pn to the power of k times an. So what is the number of factors? It's ka1 plus 1 times ka2 plus 2, or 1, all the way to kan plus 1. Okay, so is there anything we noticed here? So this equals n. So is there any relationship between n and k that we can get from this? So I'm seeing a lot of things here multiplied by k on this side. So that might lead me to take, if I take everything mod k, then that would just get rid of all these terms, right? So let's take mod k. So if I take mod k, the first term is just 1, second term is just 1, 1, so on. So equals 1. So we have n equals to 1 mod k. And this is independent of any value of a. No matter what the value of a is, n is always equal to 1 mod k. So a k-nice number is always 1 mod k. Okay, interesting. So let's do some trial and error here. It's always good to do trial and error. So let's find the first 7 nice number. So we already know that any 7 nice number must be 1 mod 7. So what's the first number that's 1 mod 7? Obviously 1, right? And so which number a to the power of 7 has exactly 1 divisor? A to the power of 7 is 1 divisor. That is obviously a equals 1, right? So 1 is 7 nice. So 1 is a 7 nice number. Okay, so what about, let's take the next 1 mod 7, 6. So a to the power of 7, it has 6 divisors. Or sorry, what? 8 divisors. 8 is the next number. So what could this be? Well, a can't equal 1, right? What about a equals to 2? Does that work? 2 to the power of 7 has, right, 2 to the power of 7 has 8 divisors. So a equals to 2 works, right? A equals to 2. Okay, so that means 8 is also 7 nice. So what about a to the power of 7? What about, let's consider now the next 1 mod 7 number, which is 15 divisors. Well, right, a equals 1 and 2 doesn't work. What about 3? 3 to the power of 7 That obviously doesn't work. What about 4? 4 to the power of 7, that's 2 to the power of 14, which does have 15 divisors. So a equals 4, interestingly, works. Okay, so it seems like the pattern I'm seeing is 1, 2, 4, powers of 2, right? So this leads me to then, let's think. I think that then, so 1 equals to 7 times 0 plus 1, right? And 1 over here equals to 2 to the power of 0. 8 equals to 7 times 1 plus 1. 2 equals to 2 to the power of 1. And 15 equals to 7 times 2 plus 1. 4 equals to 2 to the power of 2. So this leads me to think, okay, so for any number that's 1 mod 7, so it's 7 n plus 1, 2 to the power of n. If we set a equals to 2 to the power of n, then this means that, let's see, a to the 7th equals to 2 to the power of 7n, and this has 7n plus 1 factors, which is n factors. So for every value of n that is 1 mod 7, there's always a value of a that works. It's specifically 2 to the power of n. So that means every number that's 1 mod 7 is also 7 nice. So every number that's 1 mod 7 is 7 nice. And so wouldn't that work with 8 as well? So every number that's 1 mod 8 is also 8 nice, right? We just take everywhere we wrote 7, replace it with 8. So every number that's 1 mod 8 is also 8 nice. So that means the set of all 7 nice numbers is the numbers that are 1 mod 7. And the set of all n nice numbers, or 8 nice numbers, is the numbers that are 1 mod 8. And so after that, I'll leave this up to you, but after that, it's easy to count that, right? Just count the numbers less than 1,000 that are 1 mod 7 and 1 mod 8. Alright? So trial and error can really be helpful, right? It can help you figure out patterns when it's not obvious. And you probably see casework is very useful. Casework so far has been casework, prime factorization, and trial and error. Those are the 3 backbones of number theory. Alright, let's go to the next problem. So let tau of n denote the number of positive integer divisors of n. Find the sum of the 6 least positive integers that are the solutions to tau of n plus tau of n plus 1 equals to 7. This is the number of divisors of n. Okay. So obviously the number of divisors has to be an integer, right? So we have either we can have 1, 6, right? The number of divisors can't be 0, so it's either 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. And then if tau of n equals 1, then this means that n equals to 1. And this obviously means that n plus 1 equals to 2. And so this case doesn't work, because tau of 2 is not 6. And same logic applies for this last case. So we're left with these cases right here. Okay, so if tau of n equals to 2, so let's consider the first case, so 2 and 5. So this means that n is a prime number, right? And 5, so 5 is odd, and the only numbers which have an odd number of divisors are perfect squares, right? So n plus 1 equals to m squared. So if we take this, then this means n equals to m squared minus 1. If n equals to m squared minus 1, that means p, which is prime, equals to m plus 1 times m minus 1. And this is obviously not possible, unless, of course, m equals to 2, but that also doesn't work. So this case has no solutions. So now, if we move on to 3 and 4, well, 3 must mean that n is the perfect square of a prime number, And 4 must mean that n plus 1 is a perfect square, or it's either a prime number cubed or the product of two prime numbers. So q times r. So these are the only possibilities, right? So we can start by counting using the perfect squares. So if we let n equals to, or p equals to 1, this gives n equals to 1, or sorry, p equals to 2, n equals to 4, and then n plus 1 equals to 5. That obviously doesn't work. P equals to 3. This gives n equals to 9. N plus 1 equals to 10. This works. P equals to 5. N equals to 25. N plus 1 equals to 26. This works. And we can keep going down, right? And then we can find a sufficient amount of solutions to the point where we don't need to find any more. So let's move on to the next case. Would be 4, 3. This case, right, n plus 1 equals p squared, and then n equals to either q cubed or q times r. And then so we can start counting here. So if p equals to, right, 2, this means n plus 1 equals to 4, n equals to 3. That doesn't work. P equals to 3, n plus 1 equals to 9, or n plus 1 equals 9, n equals to 8. This works. P equals to 4. This means, or p equals to 5. N plus 1 equals to 25. N equals to 24. That doesn't work. And we can continue like this until we find a sufficient amount. Maybe like 3 or 4. Right? And so we have one more case, which is 5, 2. So 5 is an odd number. Right? So this means that n is a perfect square. And 2 means that n plus 1 is prime. So now we can just start with m and start counting. So, right, m equals to 1. So m, notice, is not a prime. Right, so m equals to 1. This gives n equals to 1, n equals to 2. But n equals to 1 doesn't have 5 factors, so this is false. M equals to 2. This gives n equals to 4. N plus 1 equals to 3, or 5. And 4 also doesn't have 5 factors, so this is not true. M equals to 3, and we can just keep checking until we find sufficient amount of solutions, right? And then we can combine all our answers to get the 6 small solutions, and then add them up, right? So that's the crux of that problem, right? So we're out of time for today. So you can see there is still 5 problems that we haven't done, 7 through 11. And so that is your homework for this week. And I will post the solutions either this week or next week. And I will also post these Jamboards and the recording of today's class on the Google Classroom.